Let us solve gate questions from chapter 3 of mechanical engineering. So this is gate mechanical engineering chapter 3. Now the first question is a massless beam has a loading pattern which is shown in the figure. This is a massless beam. It is a simply supported beam. It's like this, and it has a simply supported load from the center to the right half or right end. The intensity of this load is 3000 Newton per meter. Let's say that is denoted by Q, and this span is 2 meter, and this span is also 2 meter. So now we call this point as A, this point as C, and this point as B. So what is the first question? The first question is the maximum bending moment occurs at what location of the beam? So let's see the options which have been provided. Option A is B, at that point B. Option B is 2675 mm right of A. Option C is 2500 mm right of A, or option D is 3225 mm right of A. These are the four options which have been provided. So how do you find out where is the maximum bending moment? Now we know that dm by dx is equal to shear force. We know that. And dm by dx will be equal to 0 when shear force is 0, means m is a constant quantity, minimum or maximum, but it's either minimum or maximum. So let's apply that condition here. So what is the shear force in this beam? It's easy to find out the shear force. Let's say that we take a section here at this location. We take the beam again here, and the beam is like this. Yeah, so we take a section here which is at the distance of x, but because we are taking from the right, this is A, so instead of taking from here, I'll take the span from here. So I take this point, this is 2 meter, and I take another x meter from here, because I have to take from the right. I have to get the answer from the right, from A. So at this point, what is the total load which is occurring on the beam? It is 3000 into 2, which is 6000 Newton is the total force on the beam. Now the value of R1 and R2 I can find out by using this equation is 6000. So this is the equilibrium of the beam, force equilibrium, and the moment equilibrium of the beam will provide me that R1 multiplied with the clockwise moment about 2, or the R2 point C, this is support C, is R1 multiplied by 4 minus, because it's a clockwise moment, plus anti-clockwise moment because of the distributed force. So distributed force is occurring at a distance of 1 meter from C. So that is 3000 into 2 is the total force, multiplied by 1, that is equal to 0. So that gives me R1 is equal to 6000 by 4, which is 1500. So now at a distance of x, what is the shear force? If I draw the free body diagram for that portion alone, this is R1, this is x, and this is the shear force here, and this is the bending moment. So the shear force in this case will be, if I write the equilibrium of this, R1 plus, or rather R1 minus, this is 3000 into x, plus SF equal to 0. Now the condition is that shear force should be equal to 0 at that point. So what is the value of, what is the value of X when the shear force is equal to 0? I get R1 is equal to 3000 X, which means X is equal to R1 by 3000, which is nothing but 1500 by 3000, that is 0.5. So I know that at a distance of 2 meter plus X, 2 meter plus 0.5, which is 2.5 meter from the to the right of A is the maximum bending moment. So option C is the right option. So that's the first problem. Now there's a linked question, it's question number 2 for the same thing. So question number 2 is the same problem or the same figure and everything. The maximum magnitude of the bending stress is given by in megapascals, obviously. So now at that location of 0.5, what is the maximum bending moment there, or what is the bending moment there? So the bending moment is, using the same diagram we can see that the bending moment will be found out. Bending moment is anti-clockwise plus the moment because of R1 is negative minus 1500 into 2.5 and plus that span is 0.5 and the value of Q is 3000, so that becomes 1500 into 0.5 is equal to 0. So the bending moment is equal to 1500 multiplied by 2, so that is equal to 3000 Newton meter. That's the unit right now. So that's the bending moment at now, or the maximum bending moment, which is in the beam. Let's check it again. So what I'm writing is, I'm writing the equilibrium of moment at this point. This is the point some point I don't know what D, that point D. So at point D, the moment because of the bending moment is occurring there in counterclockwise direction. So that is Bm, a positive moment, plus the moment because of R1, which is a clockwise moment. So that makes it minus 1500, which is the value of R1, into the distance, which is 2.5, plus the counterclockwise moment because of the distributed force. So distributed force is 3000 Newton meter multiplied by the span, which is 0.5. So that makes it 1500 multiplied by the gap between the center of that force and the point D, which is nothing but 0.5 by 2. Sorry, this is 0.5 by 2. Right. So this is not 3500 now. So it is something else. So Bm is 1500 into 2.5 minus 1500 into 0.25. So that is equal to 1500 into 2.5 minus 0.25. So that gives me 1500 into 2.25. Sorry. That's the value of moment. But we are not supposed to find out the moment value. We are supposed to find out the stress value. So for the stress value, we have been given that the width of the beam is 30. So B is 30 and the height is 100 millimeter. So the I value is 1 upon 12 into 0.3 into 0.03 rather into 0.1 cube. So the sigma or maximum stress is M upon I into Y, which is M is 1500 into 2.25 by 1 upon 12 into 0.03 into 0.1 cube, into Y is 100 by 2 is 0.05. So I just need to solve this numerical expression. If I solve this numerical expression using calculator or whatever, I will see it is coming to 67.5 10 to power 6 Pascal or 67.5 megapascals. So that's the answer. So let's see the options which are there. Option A is 60, Option B is 67.5. Option C is 200. And option D is 225. So option B is right. Now let's solve the third problem. That problem is like this. The transverse shear stress acting in a beam of rectangular cross section subjected to transverse shear load is. Yes, that's a fundamentally important problem. Question 3. The transverse shear stress acting in a beam of rectangular cross section. So if we have a rectangular cross section like this, we know that the transverse shear stress varies like parabolic distribution, and it is 0 at the ends, top and bottom, and maximum at the center. So now what are the options given? Option A is variable with maximum at the bottom of beam, wrong. Variable with maximum at the top of beam, wrong. Variable uniform C, it is also wrong. Option D is variable with maximum at neutral axis, that is the right answer. So A, B, C and D options, this is the right answer. These three are wrong. Question 4. For the component loaded with force F shown in the figure, the axial stress at the corner point P is. Now it's a good problem again. We have a component like this. There is a it's like an L angle. There is a force F acting here. That's the center of the beam. Now this end span of the beam is L, and the cross section is like a square 2b by 2b in size. Okay, so this span is L minus B, and this length is L again. So what is asked? The axial stress at corner point P. This is the point P. What is the axial stress there? So we have to suppose this point is P. This is point P. We are supposed to find out the axial stress there. Okay. Now, how do we find out the axial stress there? Obviously, there will be two stresses acting at P. One is the bending stress. The bending stress is because of the bending moment F into L minus B, because L minus B is the span between the center of that vertical section and the point where force is acting. So the first stress, sigma 1, or let's say sigma B, which is because of the bending, is equal to the bending moment there, which is F into L minus B upon I. Now I is nothing but we know that the height and width are 2b each, so that is 2b multiplied by 2b to power 3 multiplied by b, which is y, which is half of b, 2b, right? So this is the bending stress. So if I just resolve this, I will see it is F L minus B into B upon this 12 will go up, and I have 2 into 2 into 2 into 2, so 16B to power 4. So this will be nothing but 3 by 4 F L minus B upon B cube. That is the bending stress. There is a direct stress also, direct stress at P, which is nothing but the force divided by the area of cross section, which is 2B into 2B. So that is F upon 4B square. So the total stress at P, at point P, is nothing but sigma T at P is 3 by 4 F L minus B upon B cube plus F upon 4B square. So I can further resolve this like this: FL upon B cube minus 3F upon 4B square plus F upon 4B square. So this gives me 3 by 4 FL upon B cube. This becomes minus 3 by 4 plus 1 upon 4 is minus 2 upon 4, which is F upon 2B square. That is the answer. Okay, we don't need to solve this actually like this. The options is given in terms of in this terms itself, in this itself. So this can be resolved like this. F upon 4, this is f upon 4 is a common here. I can even take b square common, f upon 4 b square, so that leaves with me L minus b upon b plus 1, right? Is this right? No, this has to be 3 here also. Yeah, so that leaves me with f upon 4b square into 3l minus 3b plus b upon b. So that leaves f upon 4b square 3l minus 2b upon b. So that gives me f upon or rather I'll simply say f into 3l minus 2b upon 4b cube. That is the answer. So which option is right? We have option A, which is f 3l minus b upon 4b cube. Option B, f 3l plus b upon 4b cube. Option C, f 3l minus 2b upon 4b cube. No, sorry, f 3l plus 4b upon 4b cube. And option D is f 3l minus 2b upon 4b cube. This is the right answer. Now let's see question number 5. Question number 5. Where is question number 5? Yeah. Question number 5 is it's an again very simple question which deals with the fundamentals. Question number 5 says a simply supported beam of span 6 meter and 75 millimeter diameter, that's a circular beam now, carries a uniformly distributed load of 1.5 kilonewton meter. And so this is the circular beam of 6 meter span and diameter of 75 millimeters. So this is question number 5. This is simply supported, so it is simply supported like this. It is carrying a uniformly distributed load like this. It's a uniformly distributed load. Its intensity is Q, which is 1.5 kilonewton per meter. That is given to us. So the value of Q is given. Now what is the maximum? Now the first question number 5 is actually what is the maximum value of bending moment. Now obviously for this case we know the answer. It is M max is nothing but Q into L square by 8. That is the answer. And if you do not remember, you can solve for it and figure out that this is the value of maximum moment. So if I just solve this, you can use your calculator to solve this problem. You will get the value is equal to 1500 into L square is 36 upon 8. So this is 9 by 2. This is 750 into 9. 750 into 9 is 9 is 9763 6750 Newton meter. That is a value. It can be converted to kilonewton meter by saying it is 6.75 kilonewton meter. That's the answer. So which is that option? Option number, oh, I don't know why this option is not occurring. Again, there's a problem with the booklet. There is no option which is 6.75 kilonewton. There is nothing there. That's the options are wrong or the data is wrong. But if the questions are, if the data provided is right, then options are all wrong. The option is this is the right answer. 6.75 kilonewton meter. That's the right answer. Now let's see question number 6. Yeah, what is the maximum value of bending stress? Bending stress is nothing but M upon I into Y. So this is a circular beam, so that gives me M 6 point, or rather I'll just say 6750 divided by I is pi by 64 into d to power 4 into y. Y is radius, so d upon 2. So this value of d is 75 millimeter. It has been provided to us, so that makes it 6750 into 37.5 upon pi by 64 into 75 to power 4. If you do the calculation using calculator, now this is, if you do not have a calculator also, you can do this problem. See, it's not very difficult to solve. Now let's see how it can be solved. You have, if this problem, and this problem can be converted to another expression, which is 64 goes to the numerator upon pi into 75 to power 4. Now see, pi and 175 can be taken out from here, which is nothing but double of 37.5. So I can say 64 into 6750 into 37.5 divided by pi into 75 cube into 75. Right, this is 75. This 75 is coming out from the power 4. So this makes it 1 and 2. Now this 2 can cancel out 64 and make it 32. Now 32, and value of pi is 3.14. So 32 is almost 10 times of that. So I can say this is 10. So 32 by pi is almost 10, around 10. So this is around 10, which is this portion is 10 multiplied by 6750 upon 75 cube. Now what is the value of 75 cube? Approximately it's around, it's slightly more than 3500. If I'm not wrong, it is because 70 or 7 third power is 343. So 75 or 7.5 third power will be slightly more than 3500 or whatever. So if I just put an approximation again, I will get something like 3.5 into 10 to power 6. No, 10 to power 5. Something like this. So this is almost 1.6 or 1.7 times of that. So we have to check which option is giving us around 160 kind of value, because this is nothing but 16 into 10 to power minus 5, which is nothing but 160 10 to power minus 6 or 160 MPa. So that's the answer, around 160. So which is that option? Option A, because option A is 162.98, option B is 325.95, option C is 625.95, and option D is 651.9. All of them are in MPa, so option A is right. So this is A, yeah, this is B. So this is the right answer, 162.96, 98, sorry. This is 98. So that's question number 6. Now let's solve question number 7. A cantilever beam has a cross section of 10 by 10 millimeter square. It carries a transverse load of 10 Newton. Yeah, so it is a cantilever beam like this. And at the midpoint of the beam, it is carrying 10 Newton concentrated force. And this is 1 meter and this is also 1 meter. So this cross section is 10 by 10 millimeter, right? Considering only the bottom fibers of the beam, which means only this fiber, this is the fiber, this fiber, this is the bottom fiber, bottom, and it's the top, this is top. So only the bottom fiber. Now here, the correct representation of the longitudinal variation of bending stress. Now, first of all, what is the bending stress in this beam? So what is the bending stress? Bending stress is sigma is equal to the moment, which is 10 by 1 upon I, which is 1 upon 12 into 0.01 to power 4 into 0.01 by 2. So this is the value of bending moment, bending stress in this beam. So if I just figure out what is the maximum bending stress, it will be 12 into 10 into 0.01 by, this is 0.01 to power 4 into 2. This 2 is coming from this 2. So if I just take this expression, I can divide this and make it 6. So this is 60 into 0.01 upon 0.01 to power 4. This makes it 3. So this is 60, and this is multiplied by 10 to power 6. So that is 60 MPa. So that's the maximum stress which occurs at the point. If I say this is point B, this is point A. So at point B, this is the maximum stress. So now how will this vary? So let's see the options which have been provided. Option A is like this. It is varying from 60 to half span and then constant. Basically it is 0 here. This is 0, this is 60. Option B is the variation is like a parabolic variation, and then after half length it is 0. This is 60. Option C is from 400 it goes to 0 at the mid span and then becomes flat at 0. And option D is it starts from 400 like a parabolic curve and goes till mid span and then becomes flat 0. So which is the right answer? Obviously D and C are wrong because the value is 400. This is 400, so they are wrong. We can just eliminate them. This is crossed out, this is also crossed out. Now the two options, the variation of bending stress. The bending stress is proportional to the force multiplied by the distance, and distance is a linear variation here. So because it's a linear variation of x, so let's say if I draw the shear bending moment diagram for this section, it will be px. So it's a linear variation. So m is proportional to px and sigma is proportional to m, right, which is proportional to px. So it has to be this way, like a linear variation. So this is wrong and this is right. Now let's see the 8th question which is there. Question number 8. Two beams, one having a square cross section and another's circular cross section. Okay, so there are two beams. One has a square cross section and another has a circular cross section. This is question 8. There are two beams. Yeah, are subjected to same amount of bending moment, right? If the cross-sectional area as well as the material of both beams are same, right, then option 1, maximum bending stress developed in both the beams is same. Now we are applying same moment to both of them, M and M, and the area is also equal. So now when the area is equal, this is M, In both of them m is applied. So area is equal. So let's say this side is a, and this radius is r here. So I know that a square is equal to pi r square. So I have a relationship between a and pi, with a and r, which is a is equal to r square root pi, which means that area is slightly more than the radius. Oh, sorry, the side of the square is slightly more than the radius. Now, what happens to the bending stress? For that, we need to know the value of I. So I square is 1 upon 12 into a to power 4. If I convert that into r, I get 1 upon 12 into r into square root pi to power 4, which is nothing but pi square r to power 4 upon 12, right? And I circular is pi by 64 pi by 4 into r to power 4. So that remains at pi by 4 r to power 4. Now see the bending moment. Sigma bending moment in square cross section is m upon I. So m upon is into ys. So ys is a upon 2. So that will be m upon is is pi square by 12 r to power 4 into ys. Ys is a by 2. So I just simplify this equation. It becomes 12m. A is r square root pi. So that I can put here r square root pi upon pi square r to power 4 into 2. This is this 2. So this cancel out 6. So this is nothing but 6 square root pi mr upon pi square r to power 4. That is a maximum stress in square cross section. Similarly, the maximum stress in circular cross section is m upon ic into yc. So this is nothing but m upon, we know what is the ic for that, it is pi by 4 into r to power 4 multiplied by r. Yc is nothing but r. So that we get, now if I invert this, it becomes 4mr upon pi r to power 4. This is the value. Now sigma s upon sigma c is 6 square root pi mr upon pi square r to power 4 divided by 4mr upon pi r to power 4. So this r to power 4 gets cancelled, mr gets cancelled, and this pi cancels the square. So this becomes 6 square root pi upon 4 pi. This is nothing but 3 by 2 square root of pi. Sorry, 3 by 2 divided by square root of pi. Now if we solve this this equation, rather let's say if we solve this this expression 3 by 2 divided by square root pi. So what is the square root of pi? What is the value of pi? It is pi is equal to 3.14, correct? So this value will be 1.5 divided by square root of 3.14. Now square root of 3.14, let's guess it, how much it will be. We can do a long calculator or we can use calculator, but guessing is also a good thing. So if you remember, the square of 18 is 326 and the square of 17 is 289. So square of 1.7 will be 2.889. So obviously, had this been 2.89 itself, the square root would have been 1.7. So this always will be something somewhere between 1.7 and 1.8. So this will be 1.5 divided by some number which is between 1.7 to 1.8, which is more than 1.5. So this will be less than 1. So the sigma c will be more than sigma s. That's the final conclusion. We can also do this problem by doing a very simple thing. We superimpose the two cross sections. So if this is the area of square, the area of circle will come something like this. This is how it will come. So the top and bottom fibers of the circular cross section will be higher than the top and bottom fiber of the square cross section, which will mean that the stress there will be slightly higher. So we don't need to even solve all this. We can just do this thing and figure out. But that's not easy thing to do all the time. So it is better to solve and check. So let's see the answers which are provided. Answer A is maximum bending stress developed in both the beams is the same. Wrong. So option A is wrong. Option B is the circular beam experiences more bending stress than the square one. That is the right answer. Option C is the square beam experiences more bending stress than the circular one. That is also wrong. And D is, as the material is same in both, the beam will experience the same deformation. Well, we don't know because there is nothing provided about the length, etc. So that also we cannot say. So that is also not correct. So only option B is the right answer, which is in circular cross section the bending stress will be higher than the square cross section. Rather, the stress in circular cross section will be higher than the stress in, or the bending stress in square cross section. So now question number 9. Yeah, bars AB and BC, each of negligible mass, support load P as shown in the figure below. Now this figure is like this. There are two pins. There is one horizontal bar and there is one inclined bar like this. This is it is point C, this is point P, and this is point A, and there is a force P. So both A and C are pins. Please see it carefully. Both of them are pins, right? Pins cannot provide a moment reaction. That we have to remember. So now what are the options for this in this arrangement? Now what happens in this arrangement? Option A, bar AB is subjected to bending. This is bar AB. It bends. But bar BC is not subject to bending. Wrong. Because both bar AB and bar BC cannot sustain a bending moment. They don't have moment fixity anywhere. They can only take forces. So this is wrong. The second option is bar AB is not subjected to bending, but bar BC is subjected to bending. That is also wrong, because they cannot take bending at all, because there is no moment fixity. There is no reaction to the rotation. Now option C is neither bar AB nor bar BC is subjected to bending. That is the right answer. So option A is wrong. Option B is also wrong. Option C is right. What does option D say? Option D says both bars AB and BC are subject to bending. That is also wrong, because bars cannot take bending at all. They don't have any moment reaction. So this is also wrong. So these are the questions which are there in chapter 3, which is about bending stresses in beams. This is also a very important chapter like chapter 2. Because bending stresses are important concepts in the design of beams, and there might be some question in GATE in this. It comes approximately almost every year. There is at least one question from this also. Sometimes they may club this with the deflections, which is the next chapter, which we'll see. But it's a good thing to practice a lot of questions from this. And this is also a fundamentally important chapter in strength of material. So please solve as many problems as you can in this